The purpose of this clip is to present the article Analytic Pavement Modelling with a Fragmented Layer, written by myself and Asmus Carr. And the article was published in the International Journal of Pavement Engineering, and I will include a link in the description to the article. The motivation behind the work is that layered elastic theory is widespread and useful for pavement analysis and design, but the theory considers continuous layers that are unbroken. And in actual pavement systems, we may encounter layers that are multi-cracked or fragmented. Here's one example. You have a road that is severely alligator cracked, and if this road is overlaid, then the cracked layer remains in the pavement system as a fragmented layer. Or if the road is milled and overlaid, but the entire layer, the existing layer, is not completely removed, then we again have a rehabilitated pavement system that includes a fragmented layer. Another case where fragmented layers may appear is when we have fractured slab technologies. For example, here where you have a fractured slab overlaid with a continuous new asphalt concrete layer. Another example of a fragmented layer is interlocking paving blocks. You can consider a layer of interlocking paving blocks as a fragmented layer. And there are many cases where the fragmented layer, the interlocking paving blocks, are in fact not at the surface but overlaid with a continuous layer, for example, here. The objectives of the study are to first analytically introduce a fragmented layer into the layered elastic theory formulation, and then demonstrate the capabilities of the new idea, and then list prospective utility cases. Graphically, we are thinking about taking a layered elastic pavement model, a standard layered elastic pavement model with several layers where the lowest layer is semi-infinite, loaded at the surface over a circular area with a uniform stress intensity that is applied vertically, and then introducing a discontinuous, fragmented or severely broken layer into the system somewhere between layer I and layer I+1. The modeling approach that is offered by the article has two types of fragmented layers. The first one is called a P-type fragmented layer. It includes two shear layers that are sandwiching a Winkler spring bed, and the K-type fragmented layer where there are two Winkler spring beds and they are connected at the center with a shear layer. The letter P stands for Pasternak because the shear layer is coming from a Pasternak foundation model, and this K-type fragmented layer is named after Kerr foundation model. In the model, in both types, K has units of force per cubic length and represents the fragmented layer vertical stiffness. Basically, it's the Winkler spring bed. Here you can see K here and here. G, with units of force per length, represents the interaction between the individual fragmented layer springs. It is basically a Pasternak shear layer. And we have an extra parameter KH, also with units of force per length cube. It represents the fragmented layer's ability to transfer shear stresses that operate parallel to the top and bottom interfaces. Both the fragmented layer formulations do not include the layer thickness. This parameter is in fact redundant because it can be indirectly incorporated in the values of the governing parameters, the other parameters I just covered. Also, there is no real meaning to stresses and strains within a layer that is fragmented, as stresses and strains refer to a continuum mechanics approach, and here we have a fragmented layer. Thus, a fragmented layer is introduced into the layered elastic theory as a new interface formulation. Here is the P-type formulation. There is a requirement that vertical stresses will be at equilibrium at the top of the fragmented layer. This is the expression that provides that. We also have a requirement that the vertical stress is in equilibrium at the fragmented layer bottom. And the equality of shear stresses above and below a fragmented layer is requested or demanded. And then lastly, we have the horizontal springs as they are taken into account here. The vertical stress equilibrium and at the top and bottom of the fragmented layer is different for the K-type formulation, but the other requirements are the same. So in case of a K-type formulation, these two expressions should replace the previous two. Here I'll demonstrate the capability of the new theory. So let's look at the fragmented layer covered by a continuous layer. Here we have a layered system where the fragmented layer is buried 50 millimeters below the surface layer. This system is loaded by a circular load with a diameter of 300 millimeters and a vertical stress intensity of 0.5 megapascal. You can think about the top layer here as asphalt concrete overlaying some old and damaged asphalt concrete that is multi-cracked or fragmented. The layer here can be thought of as a base or subbase, and here we have a subgrade, soil-like subgrade extending to a large depth. Here are the results for the surface vertical displacement or deflection of this pavement system. On the left, we have a p-type solution where the shear layer is set to 0. Basically, it means that the fragmented layer here is considered a pure Winkler foundation. The different curves here represent different values for the Winkler spring bed. K equals 0.1, 0.2, 0.5, and infinity. The values of K here are with units of megapascal per millimeter. The two curves that are shown are indicating whether the horizontal spring stiffness is 0 or infinity. If it is in between 0 and infinity, then the resulting curve should be somewhere in between the two. When the shear layer has stiffness, for example, in this case 10,000 newtons per millimeter, then the deflections change accordingly. They are smaller because we have the extra rigidity from the shear layer. Another capability demonstration is where the fragmented layer is placed at the very top, or effectively at the very top. Since the fragmented layer is an interface, it cannot be placed at the top without overlaying it with a continuous layer. But the idea is that we use a very thin continuous layer on top of the fragmented layer. Here, the continuous layer is 0.1 millimeters in thickness. So effectively, we have a situation where the fragmented layer is placed at the very top. In this case, I'm showing the results for a K-type fragmented layer formulation. Here on the left, you can see the deflection at the surface when G is 0. And this is again representing a layer system that has on top a Winkler spring bed, and the load is applied directly to the Winkler spring bed. This is how you can see the discontinuity in the deflection. And again, different curves here indicate different K values in units of megapascal per millimeter. This is the same case with a K-type fragmented layer on top, but here a shear layer is introduced with rigidity of 1000 newtons per millimeter, and you can see the effect of that on the deflection. Overall, the new theory is deemed suited for considering milled and overlaid pavements where the old fragmented and fractured and aged asphalt concrete is still retained within the new rehabilitated structure. It also applies to rehabilitated pavements where fractured slab technologies have been utilized to fracture old concrete, Portland cement concrete, and then overlay it with the continuous asphalt layers. And it could also apply to interlocking pavement blocks. For the first time, you have an analytic treatment that can capture the effect of the blocks, and there's no need, therefore, for assigning an equivalent modulus to the layer of the blocks. Thank you very much for your attention, and if you're interested in pavement mechanics, I invite you to check out my pavement mechanics lecture notes that is published now on Amazon. I will also include the link in the description below for the book.